So, why go to Europa? In a word, water. Wherever we find water on Earth, we find life. So naturally, wherever there might be liquid water out in our solar system, scientists want to go there to understand it better. Europa is an icy moon of Jupiter. It has an icy outer shell, and scientists believe that there is a salty, briny ocean that sits underneath that icy shell. And so we built Europa Clipper to go and explore and understand that better. So there's many types of measurements that scientists hope to make at Europa, and I'm sorry for the folks in the back. The letters are a little bit small, but I will walk through them. So there's two flavors here. We have in situ measurements, so those are the ones that are in yellow. In situ means taking a measurement, the thing that you're taking the measurement of, you're in contact with it. So the first one here is sampling the atmosphere of Europa. There's the dust analyzer, so looking at the dust and the plumes that are coming off of the surface of Europa, measuring the magnetic field around Europa and the plasma environment. Besides in situ measurements, we also have remote sensing measurements that we hope to make. Remote sensing is usually like a sensor or a camera that's looking at a specific wavelength of light or electromagnetic radiation. So we have something to look at the ultraviolet spectrum, infrared, visible light, so what you or I would see if we were there looking at Europa, thermal imager, and there's also using radar to map Europa. For those of you who can read the slide, the words at the top of each of the circles represents an instrument that is on board Europa Clipper. So this is what the instruments look like, and if we're going clockwise, starting from the upper left. In the upper left, we have the magnetometer, the Europa Clipper magnetometer that sits on the end of a very long boom, and you can see the people there for reference. It's a really long boom that deploys after we launch. SUDA is the dust analyzer. PIMS, there's two PIMS on board. There's a PIMS upper and a PIMS lower, and those will measure the plasma environment around Europa. ICE, WAC, and NAC are the cameras. So WAC stands for the wide angle camera, has a wide angle lens, and NAC is the narrow angle camera, has a narrow angle lens. Can zoom in on Europa. And that one sits on the end of a gimbal, so we can point it, looking at the surface of, at features on Europa. Mass specs, which is what I think is the coolest looking instrument. Mass specs is the mass spectrometer, so that's the one's going to be sampling the atmosphere. ETHEMIS is the thermal imager, UVS is looking at ultraviolet, and we have MISE here for infrared. There's one instrument that I don't have a picture of. It's called Reason. Reason is a set of antennas that sit on the solar panels, and I just couldn't find a good picture that really did it justice. So scientists work with engineers to build and design these instruments, and then there's another set of engineers that work on designing a spacecraft that can support those instruments. So here you can see where the instruments are placed around the spacecraft, and special attention here a bit to Reason, for that you can kind of see the Reason antenna and how it sits on top of the solar panel. So the spacecraft has all of the capabilities to bring the instruments to Europa and take the measurements. So it has different subsystems that support the instruments. So structures for where we place them. It has a thermal system to keep it the instruments from getting too hot or too cold. Avionics, propulsion, guidance, navigation, etc. And so each of these subsystems work together along with the instruments to meet the mission objectives. So how does this all come together? Each of these subsystems and the instruments teams, they deliver their hardware to the ATLO team. That was the team that I worked on. ATLO stands for Assembly, Test, and Launch Operations. I specifically worked on the ATLO Systems electrical team. Our primary job was to integrate the electrical hardware, and anytime we turned on and commanded the spacecraft, that was our job. But there were many other teams. We had a mechanical team, quality assurance, ground data systems, contamination control, planetary protection, all working together to build this spacecraft. So how did all this come together? It started with much smaller parts. So these were the two first pieces that got delivered to us in ATLO. On the left here, you have the vault. The vault is this box that we install all of the sensitive electronics, so the flight computers and the sensitive parts for the instruments and other electronics. The vault is built to protect and shield these electronics from the really strong radiation environment around Jupiter. The nadir deck on the right, the nadir deck, so nadir means pointing towards the surface, so the sensors that for the instruments that need to be looking at Europa are mounted on the nadir deck, and as Europa does flyby, or as Clipper does flybys of Europa, the nadir deck will be pointing at the surface. There's another institution, the Applied Physics Laboratory, that JPL partnered with. They designed and built and delivered the propulsion module. So this big cylinder that you see here, it has the hardware for the propellant and the thrusters, has the solar array actuators and the telecom hardware. The inside of the cylinder is where these big tanks sit that has the propellant for the spacecraft. And when you take the vaults in the nadir deck and you put it on top of the propulsion module, you get a fully stacked spacecraft. So the vault and the nadir deck are on the top of the spacecraft here. They're covered in MLI blanketing. That's blanketing that helps to keep the spacecraft warm. And then you can also see the high gain antenna. That's the big dish that's sitting pointing off to the side. The high gain antenna is how we will get most of the data back from the spacecraft. So once the spacecraft has been built up is far enough along, we start to do environmental testing with it. This makes sure that the spacecraft is able to work within the various environments it's going to encounter in space. So there's two here that I'm going to talk about. The first one is the electromagnetic interference, electromagnetic compatibility test. And so here you can see this Europa Clipper sitting inside of the tent, the EMI EMC tent here. So this test ensures that the spacecraft works in the presence of strong signals. So this could be a signal that's coming from outside of the spacecraft, like a fast radio burst that we just heard about, or a microwave if we brought those with us, or it could be from a signal that's generated by the spacecraft itself. So all of the parts of the spacecraft generate their own noise, and we need to make sure that if we turn on one device, it doesn't interfere with the measurements that an instrument might be taking at that time. So when we run this test, the front part of this tent gets lowered, and that allows us to control the electromagnetic field that's inside of that tent, and we can do the tests to make sure that the spacecraft works. Over on the right is Europa Clipper that's sitting inside of the 25-foot thermal vacuum simulator that we have at JPL. And thermal vacuum testing makes sure that the spacecraft will survive the vacuum environment of space. We often think of space as being really cold, but when you're talking about components of a spacecraft, some parts get really hot and some parts get really cold. And it really depends on how close that spacecraft is to the sun, which parts are facing the sun at any given time, and which parts are facing away. So the parts that are facing the sun tend to get really warm, and the parts that are facing away tend to get really cold. Surprise. And it's the thermal subsystem's job to make sure that no part gets too hot or too cold. And in the thermal vacuum testing, this chamber allows us to take all of the air out and control the temperature, so we can put it through the different hot and cold environments that it's going to experience in space. Thermal vacuum testing is one of the most grueling times in the ATLO campaign. My team and I, we spent 3 weeks around the clock, nonstop, monitoring and testing the spacecraft while it was in the chamber, and we were all very glad when we were done with that. Once we finish doing the testing and we make sure that the spacecraft will work in the environments of space, we then prepare to ship it to the launch site. So here you can see Europa Clipper sitting inside of the shipping container. It's on its side, and it's attached right here. And that shipping container will protect Europa Clipper as we ship it from Pasadena to Florida. And the way we get it there... No. Not FedEx. We work with the Air Force. So the mechanical team drove Europa Clipper in the shipping container to March Air Force Base, which is near Riverside. and the Air Force loaded it onto a C-17 and flew it to Cape Canaveral, Florida, which is where we then drove it to Kennedy Space Center, and that's where we finished working on it. So some few lucky mechanical engineers and QA engineers got to ride on this C-17. I flew economy. So one of the major integrations that we did when we were at Kennedy Space Center was to install the solar panels, and the solar panels are really big. Europa Clipper is the largest interplanetary spacecraft that NASA has built to date, and it's because of the solar panels that it's so large. When they're fully deployed, they are bigger than the length of a basketball court. And when you're standing next to them, they are impressively large, so humans for scale. So this picture was taken just after we had integrated one wing of the solar panel to the spacecraft. These panels are so big, we can only do them one at a time. We didn't have enough space to have it fully deployed in the building that we were working in. So once we finish all of the final integrations, we do the final test to make sure that we built it properly. We get the spacecraft ready to launch. So we stowed the solar panels, and here you see Europa Clipper in its final configuration, ready for launch. And it'll separate from the launch vehicle at the interface that you can see just below the solar panels there. So once we prepared the spacecraft, we then hand it off to the launch vehicle provider. In this case, it was SpaceX. SpaceX provided, NASA bought a Falcon Heavy from SpaceX to take Europa Clipper. This phase here is called encapsulation. So you take the two halves of the fairing and encapsulate the vehicle in the fairing. So the fairing keeps the spacecraft protected from Earth's atmosphere as the rocket goes from the ground up into space. And once the rocket gets out into space, the fairing separates so that the spacecraft can get off the rocket. Once you close the fairing around the vehicle, that's the last time. So this is the last time that anyone laid eyes on Europa Clipper. So it was at this time that SpaceX put the fairing, or installed the fairing on around the launch vehicle, or around the spacecraft. They then took that into their hangar to integrate onto the launch vehicle, and we were getting ready to launch. We ended up having to stand down for a few days as Hurricane Milton approached, coming from the west. So Hurricane Milton was one of the large hurricanes that hit Florida this past fall, and we had to hunker down. And where we were staying, the spacecraft had to stay in the hangar while we waited for the hurricane to go overhead. It ended up being a direct hit of Kennedy Space Center, which has been a long time since one went directly overhead. We were fortunate, though, that in our area, we didn't have very much widespread damage, and so we were able to resume work pretty quickly after the hurricane went overhead. And actually 2 days later, SpaceX was able to roll out the launch vehicle to the pad. So here you can see the Falcon Heavy on its side as SpaceX is rolling it out to the launch pad that you can see off in the distance there. So SpaceX does their launch vehicle rollouts horizontal, and then once it gets to the launch pad, they erect it vertical. And so here is Europa Clipper and the Falcon Heavy in the vertical launch position. Now, one thing you notice here, the boosters that are on the side have this kind of black char on them. And that's because SpaceX often reuses their boosters. They've gotten really good at recovering their boosters and launching them again. So these are actually the sixth time, this launch was the sixth time that these boosters were used, sixth and last time. But 2 launches prior, these boosters were used to launch another JPL mission, Psyche. JPL launched Psyche, landed the boosters. They used them actually another time in between Europa Clipper, and then the 6th time launched Europa Clipper. Clipper is so big and needed to go so fast that there was not enough fuel left for SpaceX to recover the boosters, and that's why it was their final flight. So we're now on October 14th, 2024. It's my team's responsibility to do the final spacecraft preparations before launch. We began our day 6 hours before launch. The overnight crew, the third shift, handed us a vehicle that was in perfect conditions, and we spent the next 6 hours sending the final commands to the spacecraft to get it prepared for launch. I'm not hearing the audio here, so...
You have to do your audio.
I have my audio, yeah. And liftoff of Europa Clipper on its way to Jupiter to explore icy moon Europa. All right. So this here is some of the final images of Europa Clipper, and we're going to see it there separating from the launch vehicle. So there it is drifting off into the distance. And in a little bit, it's going to turn on its radio and start talking to the ground. This is the moment that the ATLO team lives for. So with the successful delivery of the spacecraft to space and with communications established with the ground, we hand off responsibility of the spacecraft to the operations team. So our job is done. We pack up and go home. So this is me and the rest of the day of launch team who was on console. And you can see the little arrow there. So this was taken right after we reached T0 and the Falcon Heavy launched. So we were all sitting on console, and as soon as it went to 0, we ran outside so we could see it. This picture represents just a small fraction, though, of the people who worked on Europa Clipper. It's about a third of the people who worked on on my team, the ATLO systems team. There are about 100 of us who were deployed out to Florida to get Europa Clipper ready to launch, and there are thousands of people who worked on Europa Clipper over the many years of getting this ready. And in fact, actually, looking around, I can see many colleagues and friends that I worked on Europa Clipper together. So good job, everybody. We did it. And now Europa Clipper is on its way to Jupiter. It's a long journey. It's going to take it a while, and it's going to get some assistance. So actually next month, March 1st, Europa Clipper is going to fly by Mars and pick up some momentum there. It's actually coming back to Earth in December of 2026. It's going to pick up some more momentum there, and that's going to slingshot it out to Jupiter and arrive in Jupiter in about 5 years from now in April of 2030. And once it gets there, it'll start its mission to look at Europa Clipper. So if you'd like to learn more, these are 2 websites that you can go to learn more about Europa Clipper. Keeping tabs on it. This was a really exciting mission to work on. I had a lot of fun working on it, and it's great to share it with you all today. Thank you very much. Cheers.